My name is Dr. Richard Bellows. I have a PhD in chemical engineering from the University of California at Berkeley. I hold 27 U.S. patents in the areas of fuel processing, fuel cells, electrochemistry, and separations technology. In 2000, I was elected chairman of the Gordon Research Conference on Fuel Cells, and last year I was a member of a select Department of Energy committee to review the go, no-go decision on fuel processing for low-temperature fuel cells. Our approach is novel: lower capital costs, lower energy requirements, and a higher hydrogen yield. This is the actual demonstration unit. We have two electrodes, each in a separate compartment, separated by a glass frit. We have two electrical leads, which are connected to a power supply, which provides a direct current to the electrodes. The current and voltage in the test are shown on these gauges. Next, I will begin by adding deionized water to both compartments. Theoretically, hydrogen and oxygen should be evolved at a voltage of 1.23 volts. However, nothing happens at these voltages because pure water is a very poor conductor. Even at 3 volts, gas evolution is not observable. Next, I will add some concentrated potassium hydroxide to both compartments. Potassium hydroxide is a very good conductor. Again, at 1.23 volts, we still see no observable evolution of gas. However, as we raise the voltage to 3 volts, vigorous gas evolution is observed at both electrodes. The additional voltage above 1.23 volts is consumed by a combination of internal resistance in the electrolyte and in activation of the oxygen electrode. Finally, I will add methanol to the oxygen electrode compartment. This will cause the reaction to change. It is much more favorable to consume methanol than to evolve oxygen. At 3 volts, we again see vigorous evolution, but now only at the hydrogen electrode. There is no gas evolution at the oxygen electrode. This is direct evidence that the mechanism at this electrode has changed. If we reduce the voltage to about 1 volt, we continue to see hydrogen evolution. This is well below the theoretical 1.23 volts for water electrolysis. Again, this lower voltage is evidence that we are not electrolyzing water and that the mechanism at this electrode has changed. Theoretically, the methanol reaction should actually occur with 0 net voltage input. However, like oxygen evolution, methanol oxidation is kinetically slow. Hence, some additional or excess voltage is consumed as internal resistance in the electrolyte and to activate the methanol electrode. In conclusion, Gibbs has developed a novel route for producing hydrogen from methanol by conducting the reaction in an aqueous alkaline environment. This route opens unique electrochemical pathways. At moderate temperatures, methanol reforming occurs spontaneously with no external electrical input. This route can produce a uniquely pure hydrogen product. This purity will simplify hydrogen purification and produce pressurized hydrogen without expensive compressors. The process can produce directly a pressurized hydrogen product, perhaps at 2,000 to 3,000 psi without compressors, simply by using thermal input to the reactant methanol and aqueous streams, thereby reducing capital costs, reducing operating energy, and improving product yields over steam reforming.